So here is an example for how to do second class lever calculations. So a second class lever is used to lift a 350-pound load. The distance from the fulcrum to the load is 1 3/4 or 1.75 feet. The distance from fulcrum to effort is 4.5 feet. So the first thing you want to do is make sure that you know or remember what a second class lever is. So if you refer to your formula sheet, if you're not 100% sure, which I would recommend that you always have this formula sheet out, a second class lever is one with the resistance force closer to the fulcrum than the effort force. So with this illustration right here, you can see your effort force in this case is lifting up and your resistance force is pushing down. There are lots of different examples of this in the real world. The crowbar is one of the most common, but there's lots of different examples and I won't go into all of those now. So anyway, first thing we should do is label all of our variables. So our resistance load is our 350 pounds right here. So F subscript R equals 350 pounds. Our resistance distance is right here, 1.75 feet. Our effort distance is 4.5 feet. And our effort force is our unknown. So that's what we're going to end up solving for till this is all said and done. So the next step that we're going to do is we're going to sketch out the problem. So right here is my fulcrum. And a second class lever, both the resistance force and the effort force are on the same side. So I'm going to have my my resistance force closer to the fulcrum. And that's 350 pounds. And my distance from fulcrum to force is 1.75. My effort force is going to be opposing that resistance force. And this is our unknown right here. And then our distance for our effort is 4.5 feet. All right, so now we have it all sketched out and annotated. So we have enough information here that we can figure out what our ideal mechanical advantage is. So ideal mechanical advantage, again, if you refer back to the formula sheet, is always distance or effort distance over resistance distance. So we can write that right here. IMA equals effort distance over resistance distance. And then we can plug in those values. So our effort distance is 4.5 feet. And our resistance distance is 1.75 feet. And if we plug those numbers into our calculator, we end up with our IMA of 2.57. And remember, IMA or any type of mechanical advantage is a ratio, so it's 2.57 to 1 is our IMA. Okay, so now the last step in this is we still need to solve for the effort force. So to do that, we can use our equilibrium calculations where we take our resistance force times the resistance distance and set it equal to the effort force times the effort distance. So FR times DR equals FE times DE. Okay, and then we can just plug in those values. So 350 pounds times 1.75 feet equals Fe times 4.5 feet. Okay, so now we can just take this equation and start to simplify. So 350 pounds times 1.75 feet gives us 612.5. So 612.5. Remember that we got to combine our units right here. So we're now in foot-pounds, and that is equal to Fe times 4.5 feet. So now we need to isolate Fe and figure out what our effort force is. In order to do that, we can divide both sides by 4.5 feet. On this side, it cancels out. And on this side, we'll be canceling out feet. So it's 612.5 divided by 4.5. And we end up with an answer of 136.1. And now, since we canceled out our feet, our units are back into pounds. So our effort force is 136.1 pounds. And we'll come back up here and label that up here and also right here. And this problem is finished.